Right now, while you're lying there with your eyes half closed, part of you has already left, and it is never coming back. Not a thought, not a memory. Heat. Actual infrared light, leaving your skin this second, traveling outward at the speed of light in every direction at once, carrying a faint and fading record of exactly how warm you are right now. In 8 minutes, it will have crossed roughly the distance from here to the sun. By tomorrow, it will be farther from you than anything you have ever touched. It is not coming back, and there is nothing strange happening to it. It is simply obeying the same rule that governs every clock, every shadow, every orbit, and every flicker of starlight in the night sky. The rule that space and time are not two separate things politely sharing the universe between them. You were probably taught, the way almost everyone is taught, that space is the room around you, and time is the clock ticking through it. One tells you where, the other tells you when. Two completely different jobs, two completely different ideas, just happening to exist in the same universe together. Physics found something underneath that picture that very few people ever get shown clearly. Space and time are not two separate stages running side by side. They are one single structure, bent and stretched together, and the only reason the speed of light never changes for anyone, anywhere, no matter how fast they are moving toward it or away from it, is that space and time are constantly trading pieces of themselves back and forth to keep that one number fixed. Bend one and you bend the other. There is no way to touch only space or only time. There never was. This is not a thought experiment dressed up to sound dramatic. It has been measured directly, over and over, for more than a century. It has been measured in clocks flown around the planet that came back disagreeing with the clocks that stayed home. It has been measured in starlight bent visibly around the edge of the sun. It has been measured in ripples crossing the entire galaxy from black holes that finished colliding over 1 billion years ago, arriving at detectors built specifically to feel a vibration smaller than the width of a proton. Over the next while, lying exactly where you are, we are going to walk through all of it slowly. Why two synchronized clocks can stop agreeing with each other for no reason anyone can see. Why your phone's GPS would be hopelessly wrong within a single day without correcting for something most people have never heard of. What actually happens to time near a black hole, both for the thing falling in and for the person watching from very far away. And the question that even now, in 2026, with everything we have measured and confirmed and photographed, nobody has fully answered. What is space-time actually made of, underneath all of it? Settle in. None of this needs to be solved tonight. It only needs to be followed, one slow step at a time. There is an experiment, simple enough to describe in a single breath, that quietly ended one of the oldest assumptions in human history. Take two clocks, not ordinary clocks, precise ones, the kind that measure time using the vibration of atoms rather than the swing of a pendulum, accurate enough that they would drift by less than a second over tens of thousands of years left alone. Set them beside each other. Let them agree perfectly down to the billionth of a second. Then put one of them on an aircraft and fly it around the world, while the other simply stays where it is, sitting quietly on a shelf, doing nothing at all. When the traveling clock comes home, the two no longer agree. Not because one of them broke, not because turbulence or vibration knocked something loose inside the mechanism. Both clocks, examined afterward, are working exactly as they should. They disagree because they are telling the truth about two different amounts of time having actually passed for each of them. The clock that flew has counted out fewer ticks than the clock that stayed home, by a tiny but completely real and repeatable margin, measured in billionths of a second. Sit with how strange that actually is for a moment, separate from the explanation. A clock left a building, travelled around the curve of the planet, and returned having lived through less time than the version of itself that never left the room. Nothing was hidden from it. No part of the journey involved deception. It was simply true, in the most literal physical sense available, that less time happened to the clock that moved. If this were only true of clocks, it would be a strange footnote. The kind of thing you mention once at a dinner party and then move on from. It is not only true of clocks. It is true of anything that exists, anything that has a history, anything that experiences duration at all. Atoms, muscles, neurons, the slow chemical decay that we experience from the inside as aging. A traveller who circled the planet on that aircraft, standing next to that clock, would have aged by an amount that, while far too small to notice with unaided senses, was nonetheless genuinely, measurably different from the amount someone standing still on the ground aged during the same interval. They lived through less time, not felt less time, not perceived less time, lived through less of it, in the same sense that the clock counted fewer ticks. For most of recorded history, nobody thought to ask whether this was possible, because nobody thought time was the kind of thing that could be affected by where you were or how you were moving. Time was time. It happened to everyone identically, everywhere, all at once, like a great silent metronome, keeping the whole universe on the same beat. The idea that two clocks, perfectly synchronized and perfectly functional, could simply disagree about how much time had passed between them was not considered wrong. It was not considered at all. It sat outside the boundaries of what anyone thought needed checking. To understand how that boundary was finally crossed, we have to go back to a much older and much more comfortable picture of the universe. One built by a man working alone in Cambridge during a plague, who handed physics its most successful and most quietly mistaken assumption. In 1687, Isaac Newton published a book that would go on to shape roughly 2 centuries of how human beings understood motion, gravity, and the structure of reality itself. Inside it, alongside the laws of motion that still get taught in classrooms today, was a much quieter claim, stated almost as an aside, that space and time were each, in his words, absolute. Space, Newton wrote, existed in its own right, fixed and unmoving, completely indifferent to whatever objects happened to be sitting inside it. Time flowed at a constant, uniform rate, identical for every observer everywhere, regardless of motion, regardless of location, regardless of anything at all happening around it. Remove every star, every planet, every particle from the universe, and in Newton's picture, space and time would still be there, patiently waiting, like an empty stage left standing after the actors and the set have all been carried away. This was an extraordinarily useful assumption. It is hard to overstate how much of the physical world it correctly describes. Newton's framework predicted the motion of planets, the arc of a cannonball, the timing of tides, the swing of a pendulum, with an accuracy that felt, to the people using it, almost indistinguishable from certainty. Bridges were built on it. Ships were navigated on it. The orbits of the planets, once mysterious enough to be treated as divine, were reduced to clean, solvable equations. For a person living in the 1700s, doubting that time flowed at the same rate everywhere would have seemed less like skepticism and more like doubting that the floor was solid. There was one earlier crack in the picture, though, and it came not from Newton, but from a stubborn old astronomer who had already been condemned once for his ideas about the heavens. Galileo Galilei, writing decades before Newton, pointed out something subtle about motion. Imagine a sailor shut below deck on a ship with no windows, no way to look outside. If the ship is sailing in a straight line at a constant speed across perfectly calm water, there is no experiment the sailor can perform inside that cabin to tell whether the ship is moving at all. A dropped object falls straight down exactly as it would in port. Nothing tips off the sailor that water is sliding past the hull just beyond the wall. Steady motion, Galileo realized, is invisible from the inside. It can only ever be measured relative to something else. Newton absorbed this idea, but did not let it dissolve his absolute backdrop. Motion could be relative, he conceded, but space itself, the great fixed container that motion happened inside of, was not. And as for time, there was no equivalent insight at all. Nobody had a Galileo for time. A second was a second, the same one, shared by everyone, ticking forward at a single universal rate from the birth of the cosmos until whatever its end might look like. That belief sat completely unexamined for roughly 200 years, not because it was carefully tested and confirmed again and again, but because nothing in ordinary human experience ever gave anyone a reason to suspect otherwise. People do not move fast enough, relative to each other, for the cracks to show. You would need something moving extraordinarily fast to notice that time was not quite as universal as it felt. As it turned out, something was moving that fast. It had been moving that fast the entire time, sitting in plain sight, lighting up every room humans have ever stood in. Nobody had thought to ask it any hard questions yet. Light had always been treated as something that simply happened, instantly, everywhere. The way that being in a lit room felt like being lit, all at once rather than receiving light gradually from across the space. The first hint that this was wrong came not from a physicist, but from an astronomer, staring patiently at one of Jupiter's moons through a telescope in the 1670s. The moon, called Io, orbits Jupiter on a schedule precise enough to act like a distant clock, sliding into the giant planet's shadow at regular, predictable intervals. The astronomer noticed something odd. When Earth was on the far side of the Sun from Jupiter, those eclipses of Io ran consistently late. When Earth swung around to the near side, they ran consistently early. The moon itself was not changing its behavior. The only thing that made sense was that light itself took time to travel the extra distance, and that the speed of that travel could actually be calculated from the size of the delay. For the first time, light went from being something assumed instantaneous to being something with an actual, finite, measurable speed. Just a very fast one. It would take another 2 centuries before anyone understood what light actually was. That answer arrived through a Scottish physicist named James Clerk Maxwell, who spent years working out how electricity and magnetism related to each other and eventually wrote down a small, tidy set of equations describing both as 2 faces of a single underlying field. Buried inside that mathematics was something nobody had been looking for. The equations predicted that disturbances in this combined electromagnetic field should travel through empty space at one specific, fixed speed. When Maxwell calculated what that speed should be, it matched the known speed of light almost exactly. Light was not a separate mystery sitting beside electricity and magnetism. It was electricity and magnetism, vibrating together, moving as a wave. This should have been a triumphant, tidy ending. Instead, it created a deeply uncomfortable question. Every wave that physicists knew about up to that point needed something to wave through. Sound needs air. Ripples on a pond need water. Maxwell's equations gave light a fixed speed, but they never said relative to what. A wave moving through nothing, with no medium at all, simply did not fit the available picture of how the physical world was supposed to work. The natural solution, and the one almost everyone reached for, was to assume there had to be some substance filling all of space, something thin enough to be undetectable in ordinary life, but real enough to let light waves propagate through it. It was given a name borrowed from old philosophy: the luminiferous ether, the carrier of light. If the ether existed and filled all of space, then the Earth, orbiting the Sun at around 30 kilometers a second, should be plowing through it constantly, the same way a swimmer moving through still water feels a current rushing past, even though the water itself isn't going anywhere on its own. Light moving in the same direction as Earth's motion through this ether should arrive infinitesimally faster than light moving against it. The difference would be tiny, but with a sufficiently sensitive instrument, it should be detectable. In 1887, two American physicists, Albert Michelson and Edward Morley, built exactly that instrument. It split a single beam of light into two perpendicular paths, bounced each half off mirrors, and recombined them, looking for the faint shift in timing that an ether wind should produce. They expected to find it. The whole apparatus had been designed specifically to catch it. Instead, no matter which direction they pointed the device, no matter the time of day or the season, the result came back the same. Nothing. No detectable difference at all. They refined the experiment. They repeated it. They eliminated every source of error they could think of. The result never changed. The ether, the substance everyone assumed had to be there, refused to show any sign of existing. For close to 2 decades, this null result sat in physics like a splinter nobody wanted to dig out properly. Some physicists proposed patches. Perhaps objects moving through the ether physically shrank a little in the direction of motion, just enough to hide the effect that should have been detectable. The mathematics behind that patch was clever, and it actually worked numerically, but it felt exactly like what it was. A fix bolted onto a framework that was beginning to come apart at the seams, designed specifically to keep an idea alive rather than to explain anything new. It took a 26-year-old clerk working at a patent office in Switzerland, with no laboratory, no university position, and no formal access to the latest experimental equipment, to ask the question almost nobody else was willing to ask seriously. What if the null result wasn't a problem to be explained away? What if it was simply telling the truth? In 1905, Albert Einstein published a paper that took the failed search for the ether and turned it inside out. Instead of trying to rescue the idea of a fixed medium, he proposed 2 starting assumptions and refused to compromise on either of them, no matter how uncomfortable the consequences turned out to be. The first was that the laws of physics look identical to every observer moving at a constant velocity, with no special, privileged frame of reference anywhere in the universe, a more rigorous version of Galileo's sailor below deck. The second, the one that broke everything open, was that the speed of light in empty space is the same fixed number for every observer, regardless of how fast they themselves are moving, and regardless of how fast the source of the light is moving. That second assumption sounds almost reasonable until you actually try to picture what it demands. Imagine standing on a moving train and throwing a ball forward. Someone standing still beside the tracks measures the ball's speed as the train's speed plus the speed of your throw. The two simply add together, the way speeds have always behaved in ordinary experience. Now imagine, instead of throwing a ball, you switch on a flashlight while the train is moving. According to Einstein's second assumption, the person standing beside the tracks does not measure the speed of that light as the train's speed plus the speed of the light. They measure exactly the same number you would measure standing still inside the train, roughly 299,792 kilometers per second. Not faster, not slower, identical regardless of the train's motion. For that to be true, something else has to give, because speed is nothing more than distance divided by time. If everyone measures the same speed for the same beam of light, despite moving differently relative to its source, then everyone cannot also be measuring the same distances and the same durations. The numbers refuse to balance otherwise. Einstein's answer was that they don't have to balance because distance and duration were never the fixed, universal quantities Newton had assumed them to be. They bend just enough, in just the right way, to keep the speed of light constant for every single observer. Moving clocks run slow compared to a clock that stayed still. Moving objects measure shorter along their direction of travel compared to how they measure when at rest. Two events that look simultaneous to one observer can look like they happened at different times, to another observer moving differently, even though neither observer has made any kind of mistake. None of this requires faulty equipment, miscommunication, or trickery of perspective. It requires only that the universe keeps one single thing fixed, the speed of light, and lets space and time flex around that fixed point like two ends of the same stretched fabric. Pull on one end, and the other end moves too. There was no longer a meaningful way to talk about space and time as separate, independent quantities. Whatever they actually were, they were connected at a level deeper than anyone before 1905 had thought to look. Einstein's 1905 paper left physics with a strange, scattered collection of effects. Clocks ran slow, lengths contracted. Simultaneity broke apart depending on who was watching. They were all true, all confirmed by the same two starting assumptions, but they still felt like a list of separate oddities rather than a single coherent picture. It took someone else, someone who had actually taught Einstein mathematics years earlier and had not been especially impressed by him at the time, to notice that all of these effects were really just shadows of one much simpler underlying shape. In 1908, a mathematician named Hermann Minkowski stood up in front of an audience and announced, in a famous and almost theatrical line, that space by itself and time by itself were doomed to fade into mere shadows, and that only a union of the two preserved any real, independent meaning. What he had found, sitting quietly inside the mathematics of Einstein's theory, was a single four-dimensional structure. 3 dimensions of space, 1 dimension of time, fused together into something now simply called spacetime. Picture it this way. Every single thing that has ever happened anywhere, a candle being lit, a door closing, a heartbeat, a photon leaving a star, is not just a place. It is a place and a moment, combined, a single point in this 4-dimensional structure. Physicists call that combined point an event. Your life is not a path through space with time ticking along separately beside it. Your life is a single continuous line drawn through space-time itself, called a world line, tracing out everywhere you have ever been at exactly the moment you were there, stretching backward to your birth and forward to wherever it eventually ends. A rock sitting untouched on a shelf for years still has a world line. It isn't moving through space at all, so its line runs perfectly straight in the time direction, accumulating duration without ever shifting position. You, lying right where you are now, have a far more tangled world line behind you, full of bends and detours from every walk, every flight, every morning you got out of bed and crossed the room. And here is the part that connects directly back to the disagreeing clocks from earlier. The more your world line bends through space, the less of your total motion gets spent moving through time. Every object in the universe, it turns out, moves through space-time at exactly the same combined rate, the speed of light, and that fixed budget gets split between motion through space and motion through time, depending on how fast you're going. Sit still, and almost the entire budget goes into time. You age at very close to the maximum possible rate. Move quickly enough through space, and a noticeable slice of that budget gets pulled away from time, and you age very slightly less than someone who stayed still. That clock that flew around the planet was not malfunctioning. It was simply spending more of its motion on space and less of it on time than the clock that stayed on the shelf. There's a particularly important boundary built into this geometry, and it's worth holding on to because it explains why the universe can stay logically consistent even while everyone disagrees about distances and durations. Imagine a flash of light going off right where you are, right now. As the seconds tick by, that flash spreads outward in every direction at the speed of light, forming an expanding sphere. Drawn on a diagram of space-time, with space running sideways and time running upward, that spreading sphere traces out a cone shape, called a light cone. Anything inside your future light cone is somewhere your influence can eventually reach. A message you send, a signal you emit, an effect you cause. Anything outside it is somewhere you can never affect, no matter how much time passes, because nothing, not light, not gravity, not any signal of any kind, can travel fast enough to cross the gap in time. The light cone is the universe's way of protecting cause and effect. Observers can disagree wildly about distances, about durations, about whether two faraway, unconnected events happened at the same moment. What they can never disagree about is the order of two events when one of them could actually have caused the other. Effect always comes after cause, for absolutely everyone, no matter how they're moving. The flexibility of space-time has a hard edge, and that edge is the speed of light itself. If you've stayed with this through the clocks, through Newton, through the failed search for the ether, it's worth pausing for one quiet thing. Drop the time where you're listening to this right now and what it is outside your window into the comments. There's something quietly strange about it once you think about it the way we just have. Every person reading those comments later is, technically, looking at a small fossil of a different moment in space-time, frozen at the instant you typed it, while living through their own. Now, back to the geometry itself, because there is a very practical, very physical consequence of all this that is sitting in your pocket or on your nightstand right now, working perfectly, almost certainly without you ever thinking about why it has to. Time dilation, the slowing of a moving clock relative to one that stays still, is not a small correction reserved for spacecraft and particle accelerators. It happens at every speed, all the time, to everything, including you, including the chair you're sitting in, including this exact sentence being read into existence. At the speeds human bodies move at, walking, driving, even flying in an aircraft, the effect is real but almost unimaginably small, a difference measured in billionths of a second over the course of an entire flight. It only becomes dramatic, the kind of thing you could notice without atomic clocks, when something moves close to the speed of light itself.
There is a particle, born constantly in the upper atmosphere when high-energy particles from space slam into the air, called a muon. Left alone, a muon decays into other particles incredibly quickly, in about 2 millionths of a second on average. Given how fast that decay happens, and given how far up in the atmosphere muons are typically created, classical physics says almost none of them should survive long enough to reach the ground. And yet, detectors at sea level pick up muons constantly in numbers that flatly contradict that classical expectation. The explanation is the same one running through everything so far. Those muons are moving at a significant fraction of the speed of light. From the perspective of someone standing on the ground watching them fall, their internal clocks, whatever physical process inside the muon counts down to its decay, are running slow, the same way the clock on the aircraft ran slow. Enough of that decay clock gets stretched out that a meaningful fraction of the muons make it all the way down before their time runs out. From the muon's own point of view, nothing about its decay clock has changed at all. Instead, the distance through the atmosphere appears shortened, length contracted, so the trip simply takes less distance to cover. Both descriptions, the stretched time and the shortened distance, are completely valid descriptions of the exact same event, viewed from two different frames. Neither one is the real explanation, with the other one being a trick of perspective. They are both real simultaneously, because space and time are not separate enough to argue about which one gets to be the true cause. This same effect, scaled down to something almost embarrassingly small in everyday terms, is the reason your phone's GPS works at all. The satellites that beam down positioning signals are moving at roughly 14,000 kilometers an hour relative to the ground, fast enough that special relativity alone would make their onboard clocks run slightly slow, losing a few millionths of a second every day compared to a clock sitting still on Earth's surface. But those same satellites are also sitting much higher up in Earth's gravitational field than you are, in a region where gravity is weaker, and as we're about to get into, weaker gravity means time runs slightly faster, not slower. That second effect turns out to be considerably bigger than the first, and when the two are combined, the satellite clocks end up running roughly 38 millionths of a second faster per day than identical clocks on the ground. That sounds negligible until you remember that light travels about 300 meters in a single millionth of a second. Left uncorrected, that tiny daily drift would make GPS positioning errors balloon by something like 10 kilometers a day, and within about a week, your phone would be confidently directing you to the wrong city. Engineers solved this decades ago by deliberately programming the satellite clocks to tick at a slightly different rate before launch, precisely cancelling out the relativistic drift. Every single time a phone calculates a location, it is silently relying on a correction built directly out of Einstein's geometry. Nobody asked for spacetime to be real in order to find a coffee shop. It simply has to be, or the whole system falls apart within days.
This video, and the research that goes into untangling all of this slowly enough to actually follow, takes a fairly absurd number of hours to put together for something meant to be listened to half asleep. If it's helping, a like genuinely does help it find its way to someone else having one of those nights where their brain refuses to slow down. And subscribing means the next one finds you without you having to go looking for it. There's also a small, quiet way to support the channel more directly if you ever want to. Linked gently below, no pressure attached to any of it. Mostly, just settle back in because there's a particularly strange detail about something as ordinary as a wedding ring still ahead. Speaking of ordinary things hiding strange explanations, there is a metal sitting in jewelry boxes and bank vaults all over the world whose entire color is, in a very direct sense, caused by relativity. Gold is the only common metal with a distinct yellow tint. Silver is silvery. Copper is reddish from a slightly different effect. Most metals reflect visible light in a fairly even, colorless way and absorb mostly in the ultraviolet range, which is invisible to begin with, so they end up looking some shade of grey or white. Gold breaks that pattern because of how heavy its atoms are. With 79 protons crammed into its nucleus, gold creates an unusually strong electric pull on its innermost electrons, fast enough that those electrons move at a meaningful fraction of the speed of light as they orbit. At that speed, the same relativistic effects that slow down a clock or shorten a ruler start mattering at the scale of a single atom. the electrons effectively behave as though they carry more mass, which shifts the spacing between their allowed energy levels just enough that gold ends up absorbing light in the blue part of the visible spectrum instead of safely outside it in the ultraviolet. Subtract blue from white light, and what's reflected back to your eye reads as yellow. Without relativity, by most calculations, gold would look like an ordinary silvery metal, almost indistinguishable from silver on a shelf. The same underlying physics is part of why mercury is the only metal that stays liquid at room temperature. Its innermost electrons move quickly enough that the bonds between mercury atoms come out noticeably weaker than they would in a universe where Einstein's geometry didn't apply. Lowering its melting point well below the room you're lying in right now. None of this required a black hole or a particle accelerator to show up. It's been sitting quietly in jewelry stores the entire time. As strange as all of this is, special relativity, the version of the theory built from those first two assumptions about light and motion, only ever covered one specific situation. Observers moving at a constant speed, in a straight line, with nothing accelerating and nothing pulling on them. It said nothing at all about gravity, and gravity, as Einstein quickly realized, was going to be a problem, because Newton's old description of it didn't fit the new picture of the universe even slightly. In Newton's framework, gravity acted instantly across any distance with no delay whatsoever. If the sun somehow vanished this instant, Newtonian gravity says Earth would feel the absence and fly off in a straight line immediately. At the very same moment, the sun disappeared. But Einstein had just spent years establishing that nothing, no force, no signal, no information of any kind, can travel faster than light. Light takes a little over 8 minutes to cross the gap between the sun and Earth. If gravity is a real physical influence, and nothing can outrun light, then gravity has to take time to propagate too. Something had to be wrong with treating it as instantaneous, which meant something had to be wrong, or at least incomplete, in how gravity itself was being described. The breakthrough came from a thought experiment so simple it almost feels unfair to call it the foundation of an entire theory. Picture someone falling, in free fall, off the side of a building. While they're falling, before they hit anything, they don't feel their own weight at all. If they happened to be holding a set of keys and let go of them mid-fall, the keys wouldn't drop away from their hand or shoot upward. They would simply hover right where they were released, falling at exactly the same rate as the person holding them. From the falling person's point of view, for those brief seconds, gravity has effectively vanished. This is the exact same experience an astronaut has on board a space station. They are not floating because gravity has switched off up there. Earth's gravity at that altitude is still almost as strong as it is on the ground. They're floating because they and the station around them are continuously falling toward Earth together, just moving sideways fast enough to keep missing it, forever circling instead of landing. Einstein took this observation and pushed it as far as it would go, into what he later called the happiest thought of his life. If being in freefall feels indistinguishable from floating in empty space with no gravity at all, and if being inside an accelerating rocket feels indistinguishable from standing still on a planet's surface, then acceleration and gravity are not just similar. They are, locally, the exact same thing, described two different ways. And if acceleration is known to affect space and time, which special relativity had already shown, then gravity, being equivalent to acceleration, had to affect space and time as well. Gravity could not be a simple force reaching across an untouched passive background. It had to be doing something to the background itself, It took Einstein roughly 8 more years of brutally difficult mathematics, much of it borrowed from a branch of geometry he'd never formally studied and had to learn from a mathematician friend, to turn that insight into a finished theory. What he arrived at in 1915, general relativity, makes a claim that still sounds almost too simple for what it explains. Mass and energy curve spacetime, and objects moving through that curved spacetime follow the straightest path available to them, a path called a geodesic. Gravity isn't a force reaching out and grabbing things. It's geometry. A planet orbits a star not because some invisible hand is constantly tugging it inward, but because the star's mass has bent the surrounding space-time. And the planet, simply trying to travel in the straightest possible line it can, ends up tracing out a curve, because in that region, a curve is what straight has come to mean. The image most people have encountered for this, a heavy ball resting on a stretched rubber sheet, creating a dip that smaller balls roll toward, is useful as a first picture. But it quietly misleads people in an important way. It only shows space curving, and it relies on an outside force, ordinary Earth gravity acting on the rubber sheet itself, to make the dent in the first place, which is exactly the thing the picture is supposed to be explaining away. The deeper and stranger truth is that most of what you feel as gravity on Earth's surface right now isn't really coming from the curving of space around you. It's coming from the curving of time. Clocks closer to a massive object run measurably slower than clocks farther away, and the straightest possible path for you through that distorted timing, the geodesic your body naturally wants to follow, points downward, toward the ground. The mattress, or the floor, or whatever you're resting on right now, isn't fighting against a pull. It's interrupting a path. You're not being pulled down. You're being prevented from following the straightest route available to you through a region where time itself runs faster the higher up you go. A theory this strange needed to prove itself against something real, and it happened to have a stubborn, decades-old mystery sitting right there waiting for it. Mercury, the closest planet to the Sun, does not trace out a perfectly repeating ellipse around its orbit. The point of its closest approach to the Sun, called its perihelion, slowly drifts around, a tiny bit further each orbit. Astronomers had already accounted for almost all of that drift using ordinary Newtonian gravity, by carefully calculating the small tugs from every other planet in the solar system. Almost all of it. A small leftover amount, just 43 arcseconds per century, a sliver of an angle too small to picture without a diagram, refused to be explained. For a while, the leading guess was that there had to be another small planet, even closer to the Sun than Mercury, tugging on it from somewhere astronomers simply hadn't spotted yet. It was given a name in advance, Vulcan, and searched for seriously for years by several astronomers. It was never found because it was never there. When Einstein finally ran Mercury's orbit through the equations of general relativity, the missing 43 arcseconds appeared on their own, falling directly out of the curvature of space-time near the Sun, with no invisible planet required at all. That was a satisfying result, but it relied on data that already existed, which always leaves a small opening for a skeptic to wonder if the theory had simply been bent to fit a known answer after the fact. What general relativity needed was a genuine prediction, something nobody had measured yet, that could either confirm the theory or quietly bury it. It made one almost immediately. If mass curves space-time, then light itself, despite having no mass at all, should still follow that curvature, bending visibly as it passes close to something as massive as the Sun. Testing that prediction required an unusual kind of patience. stars near the sun's position in the sky are completely invisible in ordinary daylight, drowned out by the sun's own glare. The only window to see them is during a total solar eclipse, when the moon briefly blocks the sun's disk entirely. In May of 1919, two separate expeditions, one travelling to the island of Principe off the west coast of Africa, the other to Sobral in Brazil, set up telescopes to photograph the stars surrounding the darkened sun during exactly such an eclipse. Those photographs were later compared against images of the same patch of sky taken months earlier, when the sun was nowhere near them. The stars had shifted position by an amount that matched Einstein's prediction for how strongly the sun's gravity should bend their light. When the results were formally announced later that year, Einstein went, almost overnight, from a respected physicist to arguably the most famous scientist alive, his face appearing in newspapers around the world that had, until that point, mostly ignored theoretical physics entirely. That same bending of light has since become one of the most useful tools modern astronomy has, under the name gravitational lensing. Massive galaxies and galaxy clusters bend the light of whatever lies behind them, sometimes stretching a distant galaxy's image into a faint arc, sometimes smearing it into multiple distorted copies arranged around the foreground mass. Astronomers now use this effect deliberately, the way you might use a known lens to study galaxies far too faint and far too distant to observe any other way, and even to map out the location of dark matter, which gives off no light of its own, but still bends spacetime exactly as any other mass would. A century after a handful of astronomers crouched over photographic plates during an eclipse, the bending of starlight has become a genuine measuring instrument pointed at the entire universe. If curving spacetime gently is enough to bend starlight and shift a planet's orbit, it's worth asking what happens when you stop being gentle about it. What happens if you take an ordinary amount of mass and compress it down, smaller and smaller, until the curvature it produces stops being a gentle dip and starts becoming something closer to a wall? In 1916, just months after Einstein finished general relativity, a German physicist named Karl Schwarzschild, working through the mathematics while serving on the front lines of the First World War, found an exact solution to Einstein's equations describing the spacetime around a perfectly spherical mass. Buried inside that solution was something strange. For any given mass, there exists a specific radius, now called the Schwarzschild radius, at which the surrounding spacetime curvature, on paper, becomes infinite. For the Sun, that radius works out to about 3 kilometers. For Earth, it's smaller than a marble, somewhere around 9 millimeters across. Since neither the Sun nor Earth is anywhere close to being compressed down to that size, the strange mathematics seemed, for decades, like nothing more than an odd artifact, a kind of mathematical ghost with no physical reality behind it. Einstein himself argued more than once that nature would simply never allow matter to actually be squeezed past that point. He was wrong about that, and it took until 1939 for anyone to demonstrate it convincingly, when physicists modelling the death of a sufficiently massive star showed that there was, in fact, nothing in known physics capable of stopping the collapse once it passed a certain mass threshold. No pressure, no force, no exotic effect could hold the dying star up against its own gravity. It would keep collapsing, past the point where any known form of matter could resist, down past that Schwarzschild radius, into whatever lay beyond it. We now call the boundary marked by that radius an event horizon, and the object it encloses a black hole. The name wouldn't actually be coined until decades later, but the physics describing it had been sitting in the mathematics since 1916, waiting for anyone to take it literally crossing an event horizon is, by the mathematics, almost disappointingly uneventful for whatever is doing the crossing. There's no wall, no barrier, no sudden jolt marking the boundary from the inside. For a large enough black hole, an observer falling in might not notice anything dramatic happening locally at the exact moment they cross. Their own clock keeps ticking normally, from their own point of view, right up until the geometry inside eventually becomes too extreme for anything, including the observer, to survive intact. What makes the event horizon a true point of no return isn't a physical wall. It's that every possible future direction inside it points further in. There is no longer any path for light or for anything else that leads back out. From far away, the view looks completely different, and this is where time near a black hole becomes genuinely unsettling rather than just abstract. Watch something fall toward an event horizon from a safe distance, and you will never actually see it cross. As it approaches, its light reaching you takes longer and longer to climb back out of the deepening gravitational well, stretching toward longer, redder wavelengths and growing dimmer. The image of the falling object appearing to slow down more and more, fading rather than vanishing, frozen in an ever-dimming approach that never quite finishes, at least from where you're standing. The object itself is not experiencing any of that stretching from its own side. Two observers, watching the exact same event, walk away with descriptions of it that don't even agree on whether it finished happening yet. Space and time, already shown to bend under ordinary gravity and ordinary motion, simply bend further and further the closer you get to an event horizon, until the disagreement between perspectives becomes total. If you're still here, drop down where you're listening from and what time it is for you right now. There's something quietly comforting about scrolling back through one of these later and realizing how many different nows were involved in people listening to the exact same words. If space-time can bend, stretch, and trap light, the next question almost asks itself, can it move? Not the things inside it, space-time itself, the geometry, the fabric, rippling the way the surface of a pond ripples after something disturbs it. Einstein's equations said yes, almost immediately after he finished them in 1915, predicting that violently accelerating masses should send ripples outward through spacetime at the speed of light, alternately stretching and squeezing space as they pass through it. Einstein himself spent years uncertain whether these gravitational waves were a genuine physical prediction or simply another mathematical artifact, the kind that looks meaningful on paper and means nothing in reality. The trouble was scale. By the time a gravitational wave from anything astronomically interesting reaches Earth, it has spread out across such an enormous volume of space that its effect on anything here is almost laughably small. A wave from two black holes spiraling together and merging more than 1 billion light-years away, releasing more energy in a fraction of a second than every star in the visible universe combined, arrives at Earth having stretched and squeezed space by less than 1/10,000th the width of a single proton, measured across a detector arm several kilometers long. Detecting that is not simply a matter of building a sensitive instrument. It requires building one of the most sensitive instruments ever constructed by anyone, anywhere, for any purpose. That instrument exists in the form of giant L-shaped laser detectors with arms stretching kilometers in each direction, splitting a laser beam down each arm, bouncing it off mirrors and recombining it to look for the impossibly tiny mismatch a passing gravitational wave would create. On the 14th of September, 2015, after years of false starts and patient waiting, one of these detectors picked up exactly that signal. A brief, rising chirp lasting a fraction of a second, matching almost perfectly what theory predicted two black holes, each roughly 30 times the mass of the Sun, would produce in the final instance before merging into one. The signal had been traveling for well over 1 billion years before it reached Earth, a literal physical ripple in space-time itself, carrying information about an event that finished before complex life had even fully established itself on this planet. When the detection was confirmed and announced the following year, it was the first direct evidence that space-time is not a passive backdrop, quietly hosting the universe's events. It participates, it can be disturbed, and it carries the memory of that disturbance, unaltered, across distances that make 1 billion years sound almost casual. Since that first detection, the network of gravitational wave observatories around the world has caught dozens more such events, mostly merging black holes, occasionally merging neutron stars, each one adding another data point to a picture of the universe that simply did not exist as observable evidence before 2015. Just this past year, researchers combing back through some of these collision signals have started reporting faint patterns that might be connected to dark matter itself, distortions in the gravitational waves that don't quite match what an ordinary merger alone would produce. Nobody is claiming that mystery solved yet, and it's worth being honest about that rather than overselling it. But it's a genuinely live thread in physics happening right now, in 2026, built entirely on top of a kind of evidence that didn't exist a decade ago. As strange as a rippling fabric of space-time is, the largest version of this story isn't about ripples at all. It's about the entire fabric slowly, steadily growing. In the early 1920s, a Russian mathematician named Alexander Friedmann, and shortly afterward, a Belgian priest and physicist named Georges Lemaitre, working independently, found solutions to Einstein's equations describing a universe that wasn't fixed in size at all. It could expand. It could contract. At the time, this ran directly against the prevailing assumption, shared by Einstein himself, that the universe on the largest scales was simply static, the same yesterday, today, and forever. Lemaitre went further, proposing that if the universe truly was expanding now, running the process backward in time should lead to an earlier era when everything was compressed into a far smaller, far denser state. The observational confirmation came from an American astronomer named Edwin Hubble, who by the late 1920s had measured the light coming from a large number of distant galaxies and noticed something consistent across nearly all of them. Their light was shifted toward longer, redder wavelengths, a phenomenon called redshift, and the amount of that shift increased with distance. The most natural explanation was that those galaxies were moving away from us, and that the farther away a galaxy sat, the faster it appeared to be receding. It's worth being careful about how to picture this, because the easiest mental image is also slightly wrong. The galaxies are not, for the most part, racing outward through a fixed, unmoving space, the way debris flies outward from an explosion. The space between them is what's growing. A useful, if imperfect, comparison is a loaf of raisin bread rising in an oven. As the dough itself expands, every raisin drifts farther from every other raisin, not because the raisins are crawling through the dough, but because the dough between them is stretching. On the largest scales, galaxies are the raisins, and space-time itself is the dough. There is a second, even older piece of evidence sitting in the sky confirming this picture. Discovered almost by accident in the mid-1960s by two radio engineers trying to track down an annoying, persistent hiss of static in their antenna that refused to go away no matter where they pointed it or what time of day they tried. That faint, uniform background noise turned out to be leftover radiation from an era roughly 380,000 years after the universe's earliest moments, when it had cooled down enough for the first stable atoms to form and for light to finally travel freely instead of constantly scattering off a dense, opaque plasma. That ancient light, stretched enormously by billions of years of cosmic expansion, now arrives as faint microwave radiation coming from every direction, in the sky almost uniformly, with tiny variations in temperature, smaller than 1 part in 100,000, that mark the earliest seeds of every galaxy, every star, and every planet that would eventually form, including the one you're lying on right now. All of this, the bending light, the dilated clocks, the rippling fabric, the slowly stretching cosmos, points toward one final and genuinely uncomfortable idea. One that brings us all the way back to the warmth that left your skin a few minutes ago and is, by now, somewhere well beyond where you could ever reach it again. In Newton's universe, there was a single, shared now stretching across the entire cosmos at every instant. One universal moment, the same for everyone everywhere, even if nobody had any practical way to compare notes across vast distances. Special relativity quietly dismantled that idea, and it's worth being precise about how. Two distant events that one observer judges to have happened at exactly the same moment can be judged by a second observer moving differently relative to the first, to have happened at different times entirely, with one event genuinely earlier than the other. Neither observer has made an error. Neither measurement is somehow less correct than the other. They are simply slicing the same four-dimensional space-time into space and time along different angles. The way two people looking at the same hillside from different elevations will describe different ridgelines and different slopes without either of them having seen a false version of the hill. This leads to an interpretation of relativity that many physicists take seriously, called the Black-Block universe. In this view, the past, the present, and the future are not separate categories where the past has been used up. The future hasn't happened yet, and only the present genuinely exists. Instead, every event that has ever occurred, anywhere, at any time, is treated as equally real, all of it existing together as part of one fixed four-dimensional structure, the way every frame of a film exists on the reel at once, even though your viewer only ever experiences one frame at a time as the present. Nothing about this interpretation is fully settled, and physicists and philosophers continue to argue over what it actually means for things like memory, free will, or the felt experience of time moving forward at all. What relativity does establish clearly, without much room for argument, is that there is no single universal slice of now, cutting cleanly across the entire universe that every observer, everywhere, would agree on. The present, as a shared cosmic moment, simply isn't part of the physics. It's something added afterward, by minds built to experience change in a particular order. This is, in a very real sense, exactly what's true of that warmth that left your body at the start of all this. It's not gone in the way a thought is gone once you stop thinking it. It still exists, as a fixed event in space-time, the moment it left your skin permanently recorded into the geometry of the universe, just no longer reachable by you, drifting further from any possible influence with every second that passes. Somewhere, eventually, far enough in the future and far enough away, it might brush past something that could, in principle, detect it. A final faint trace of this exact moment arriving as the dimmest possible whisper of warmth. By then, you will be somewhere completely different on your own world line. But the moment itself, this one, right now, doesn't disappear once it's passed. It simply recedes, fixed forever at its place in space-time. the way every point on the four-dimensional structure stays exactly where it was, regardless of how far your own now eventually travels from it. There's one more thread inside Einstein's equations that deserves mention before we get to the part nobody has solved yet, because it's the part that tends to keep people awake, turning the idea over rather than helping them drift off, which feels worth being honest about. The equations of general relativity are, mathematically, far more permissive than most people realize. They don't just allow space-time to curve gently around planets and severely around black holes. Under certain extreme and almost certainly unrealistic conditions, they allow space-time to curve back on itself entirely, looping a path through time into a closed circle that returns to its own starting point. In 1937, a Dutch mathematician named Willem Jacob van Stockum found a solution to Einstein's equations describing a hypothetical universe made of rotating dust, and discovered that certain paths through that rotating spacetime could loop all the way around and rejoin themselves earlier in time than they started. 12 years later, the logician Kurt Gödel, working alongside Einstein himself at Princeton, found a similar rotating universe solution as what he described, in his own dry way, as a kind of birthday gift for his friend. Einstein, by his own account, found the result genuinely disturbing. These so-called closed time-like curves were not loopholes or errors in the mathematics. They were legitimate solutions to the same equations that correctly predicted Mercury's orbit, the bending of starlight, and the gravitational waves detected in 2015. Nothing in the equations themselves forbids them. What does seem to forbid them, at least according to most physicists' best current understanding, is the rest of physics surrounding those equations. Our universe shows no evidence of being a rotating mass of dust, and constructing the kind of extreme exotic conditions that would be needed to actually warp ordinary spacetime into a closed loop. Things like negative energy density, a form of matter that has never been observed and may not be physically possible to produce in any usable quantity, appears to be far beyond anything achievable, possibly even in principle. Stephen Hawking later proposed what he called chronology protection, the idea that the universe might have some deeper mechanism that always intervenes to prevent a genuine time loop from ever fully forming, snuffing it out with quantum effects the instant it gets close. Nobody has proven that conjecture either way. The honest state of the field, even now, is that the equations permit time travel into the past under certain bizarre and likely unreachable conditions, and nobody currently knows whether some deeper law of physics rules it out completely, allows it in some heavily restricted form, or simply hasn't been encountered yet because nothing in the observable universe gets anywhere close to the conditions required. A closely related idea, found in the very same year as special relativity's strangest implications were still being worked out, came from Einstein and a colleague named Nathan Rosen in 1935, who discovered that the equations of general relativity also permit a kind of bridge connecting two distant, separate regions of spacetime, a shortcut now generally called a wormhole. The original version Einstein and Rosen found turned out to be unstable, collapsing closed faster than even a beam of light could cross through it, which made it physically uninteresting as a transportation device, even though it was mathematically real. Since then, physicists have continued finding other wormhole-like solutions in the equations, some of which only stay open if propped apart by, again, that same exotic negative energy matter nobody has ever produced or observed. As things currently stand, a usable wormhole remains a legitimate mathematical possibility and an entirely unconfirmed physical one, sitting in roughly the same category as closed time-like curves, permitted by the equations, unconfirmed by anything we've ever measured, and probably, though not certainly, blocked by some deeper physical constraint still waiting to be identified. This matters for more than curiosity. If shortcuts through space-time are truly impossible, then the speed of light is an absolute ceiling on how civilizations, including ours, could ever spread or communicate across the galaxy. And the universe is very likely full of isolated pockets of life and intelligence, each one effectively alone, separated by gulfs of space simply too vast to cross within any meaningful span of time. If some loophole does eventually turn out to be physically realizable, even an extraordinarily difficult one, that changes the answer to one of the oldest questions humans have asked while looking up at the night sky. Nobody currently knows which of those two futures we actually live in. The equations themselves stay quiet on the matter, the same way they stayed quiet for decades about black holes, right up until the day someone finally took the leftover mathematics seriously enough to ask what it would mean if it were real. There's a separate, equally open question hiding in how the universe began. One that this entire framework runs straight into and then, abruptly, stops being able to answer. If general relativity is run backward from the present moment, tracing the expansion of the universe in reverse, everything converges toward a single point, roughly 13.8 billion years ago. A moment of essentially infinite density and infinite curvature that the equations themselves cannot actually describe, because dividing by zero in any form simply breaks the mathematics. Physicists call this the initial singularity, and it should be read less as a confirmed description of an actual infinitely dense point, and more as a very precise, very honest signpost that says the theory has run out of road here, and something else, some deeper framework nobody has finished building yet, is needed to say what genuinely happened in that first sliver of existence. A related idea called cosmic inflation, proposed in the early 1980s, suggests that in an unimaginably brief fraction of a second after that beginning, space itself expanded by an enormous factor, smoothing out the early universe and seeding the tiny variations later found in that ancient background radiation. Inflation explains a great deal of what's observed, but it doesn't actually resolve the deeper singularity problem. It just pushes the moment of true mystery slightly further back, behind an even thinner curtain. Some physicists have proposed that inflation, once started, may never fully stop everywhere at once, spinning off countless separate pocket regions that each settle into their own version of physical laws, an idea sometimes called eternal inflation, occasionally described, slightly more dramatically than the data currently supports, as a multiverse. It's a serious, actively studied idea among working physicists, not a fringe one, but it's also one that, by its very nature, may never be directly testable, since anything happening outside our own observable patch of universe is, almost by definition, forever beyond the reach of any signal that could ever reach us. And now we arrive at the part where this whole story, which started with clocks disagreeing and travelled through bent starlight and rippling geometry and an expanding cosmos, hits its genuine, honest, unresolved wall. Not a wall science is embarrassed about. A wall it knows is there, can measure from both sides, and has not yet found a way through. General relativity describes spacetime as a smooth, continuous fabric that curves in response to mass and energy. It is one of the most precisely tested theories in all of physics. Quantum mechanics, the other great framework built over the 20th century, describes how the universe behaves at the smallest scales. The behavior of individual particles, the probabilistic nature of measurement, the strange way that particles can exist in superpositions of multiple states at once and only resolve into a single outcome when observed. It is also one of the most precisely tested theories in all of physics. Both of them work. Both of them have been confirmed by experiments, repeatedly, to extraordinary levels of accuracy. The problem is that they fundamentally disagree about the nature of reality, and wherever both of them should apply at the same time. Inside a black hole, for instance, or at the precise moment of the universe's beginning. Neither one works correctly on its own, and no theory yet exists that successfully combines them into a single framework. Quantum mechanics says that space and time are smooth, fixed, passive backdrops against which particles do their strange probabilistic dance. General relativity says that space-time is not fixed or passive at all. It curves, ripples, and stretches in response to everything inside it. Quantum mechanics says that quantities like energy come in discrete, lumpy packets called quanta, with the smallest possible unit below which nothing finer exists. General relativity uses equations that only work when spacetime is smooth and continuous, with no smallest unit, no smallest possible distance, no granularity of any kind built in. These two descriptions of the universe are in genuine, irreconcilable tension with each other at the deepest level, and they produce nonsensical, infinite answers when applied together to the places where both should matter most. The most developed attempt to resolve this tension goes by the name string theory, which proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, one-dimensional, vibrating strings of energy, and that the different particles physicists observe are really just the same underlying strings vibrating at different frequencies. The way different notes can be coaxed from the same violin string by changing its tension. One of the most appealing features of string theory is that it naturally produces a particle with exactly the properties a quantum carrier of gravity would need to have, something called the graviton, without it being added by hand. String theory also requires the universe to have significantly more dimensions than the three of space, and one of time we ordinarily experience, with the extra dimensions curled up so tightly that they're invisible at any scale humans have ever been able to probe. String theory has been developed intensively for decades by some of the most talented physicists alive. It has also never produced a unique, testable prediction that has been confirmed by experiment. There are versions of it. Estimates range into an almost impossibly large number, sometimes written as 10 followed by 500 zeros, that each describe a different universe with different physical constants, different particles, different effective laws of nature. The framework is mathematically rich, internally consistent in the versions that have been checked, and genuinely fascinating as a piece of abstract mathematics. As a physical theory of the universe we actually live in, the honest answer is that it remains unconfirmed, and the question of whether it even makes unique testable predictions about this universe specifically is still actively disputed. A separate approach called loop quantum gravity proposes something more direct, that space itself is not smooth and continuous at the smallest scales, but granular, made up of discrete, indivisible chunks of geometry, the way matter is made of atoms rather than being a truly continuous fluid. On this picture, there is a smallest meaningful unit of space, called the Planck length, and a smallest meaningful unit of time, the Planck time, below which the concepts of distance and duration simply stop applying. The theory makes genuine predictions about what should happen to high-energy light traveling across cosmological distances, predictions, in principle, testable by certain observations of gamma-ray bursts from distant galaxies. Several such tests have been performed, and the results so far have not definitively confirmed the granularity loop quantum gravity predicts, but they also haven't ruled it out entirely. The theory is a serious, ongoing research program with real mathematical depth and a genuine commitment to making its ideas testable rather than retreating into untestability. It just hasn't been confirmed yet either. There are other, less developed approaches. Some physicists have explored the idea that space-time itself is not fundamental at all, that it's something that emerges at large scales from some deeper underlying structure, the way temperature emerges from the average motion of countless individual molecules, real and useful as a description at one level while being built from something entirely different below. On these views, asking what space-time is made of is a little like asking what a temperature gradient is made of. The answer involves zooming out from the level where the description applies and looking at what's actually doing the building. Some of the most interesting recent work in this direction connects space-time geometry to something called quantum entanglement, the strange phenomenon by which two particles separated by any distance can remain correlated in ways that seem to violate any ordinary idea of locality. Some calculations suggest that the smooth geometry of space-time, as described by general relativity, might actually emerge from the pattern of entanglement between quantum degrees of freedom arranged along the edges of regions of space. A connection that, if true, would mean the fabric of the universe is, at some deep level, woven from something closer to quantum information than to anything material. This is genuinely frontier research, not a consensus view, and the people working on it are careful to describe it as such. But it has the quality that the best physical ideas tend to have. It connects two things that seemed completely unrelated, explains both of them in terms of something more fundamental, and opens new questions that couldn't even have been clearly stated before the connection was made. And you are a small, temporary, extraordinarily complex knot in the middle of it, right now, on the edge of sleep, carrying more information about the universe in the pattern of your neural connections than most objects in the observable cosmos carry in their entire structure. That's not a motivational sentiment dressed up in physics language. It's just what's true, stated plainly. The universe made something capable of understanding the universe, and that thing is you. And you are doing it right now, even if you're mostly asleep. The warmth is still moving outward. The moment is already fixed. Sleep.